Hello, my name is Annetta Davoli, and I'm a student researcher in the 2025 OREU program at Texas A&M. Today, I'll be presenting my final update on my project, but before I begin, I'd like to first thank my mentors, Dr. Demkovic and Dr. Blaschk, for their guidance. I'd also like to acknowledge Los Alamos National Laboratory and Texas A&M for sponsoring this research. Before beginning, it's important to understand a few key concepts. Dislocations are linear defects in a crystal structure, which allow materials to deform using much less stress than otherwise possible. The image on this slide shows a model of a dislocation that intersects free surfaces in a crystal, and its movement along the glide plane is known as glide. The main goal of this project is to determine whether intersections with free surfaces restrict dislocations in magnesium to subsonic gliding speeds. This question is motivated by the scientific debate over whether dislocations in solids can exceed the speed of sound, and it matters for predicting how materials behave under high strain rates, such as during explosions or high-speed impacts. Previous simulations by Deng et al. Show that prismatic edge dislocations in magnesium can reach supersonic speeds. However, it's unclear how intersections with free surfaces might affect that. Previous research by Dong and Demkovic show that dislocation intersections with free surfaces in copper, a face-centered cubic metal, cause new dislocations to nucleate, preventing it from reaching supersonic speeds. This project will determine if this process also occurs in magnesium, which is a hexagonal close-packed metal. To carry out this project, I used molecular dynamics, a simulation technique to predict the motion of atoms over time, based on a model of the physics governing interactions between atoms. Molecular dynamics simulations were used to model a single dislocation intersecting free surfaces. A constant stress was applied to drive dislocation glide, and the resulting velocity was then calculated. By repeating the simulations at multiple stress values, a stress-velocity relationship was constructed, and a plot showing dislocation gliding velocity versus applied stress was created and used to determine whether dislocation velocities can exceed the theoretical limiting velocity under these conditions. Large-scale atomistic simulations were run using the LAMMPS molecular dynamics software package, and all simulations were run on the high-performance research computing machines at Texas A&M University. For analysis, I used MATLAB to post-process data and create plots of dislocation velocity versus applied stress. I also used OVIDO to visualize atomic structures and better understand dislocation behavior near free surfaces. All interactions between atoms were represented by the interatomic potential for magnesium, developed by Wu et al. In 2015. Before performing any simulations, it was important to validate the Wu potential to ensure it was an accurate model of dislocation behavior in magnesium. First, I generated the energy versus volume curve, shown on the left. To do this, I inputted a perfect HCP magnesium crystal and ran a LAMMPS code to change the volume of the system until it reached a relaxed energy state, and then used the output to create the plot using MATLAB. The minimum of the curve corresponds to the cohesive energy, which matched the one predicted by the Wu potential. I also calculated several key properties: the bulk modulus, elastic constants C11 and C33, as well as free surface energies. These are all important for understanding how magnesium responds to stress and deformation, especially near surfaces. The values I obtained all agree with those reported in Wu et al., confirming that the potential is reliable to study dislocation motion. I then moved on to familiarizing myself with the dislocation model. Using LAMMPS output quantities, which include centrosymmetry, nearest neighbor analysis, and per atom potential energy, I was able to identify key structural features of the model in OVIDO. The image on the bottom left shows magnesium's atomic structure, with all perfect HCP atoms suppressed to clearly visualize the dislocation. The two free surfaces appear on the left and right sides. The blue atoms in the center make up the stacking fault, while the atoms bordering it along the top and bottom are the Shockley partial cores. I then calculated defect energies associated with each feature. I started by reading atomic energy data from LAMMPS into MATLAB, then summed the potential energies of atoms in the defect regions and subtracted the energy of an equivalent perfect crystal. The table shows the computed energies normalized by length or area appropriately. These results help me understand the energetics of the system and may also serve as useful reference points in the future. It's also important to understand the two simulation setups I used and how the different boundary conditions in each can affect dislocation behavior. In both cases, I modeled a basal edge dislocation with its line direction along the x-axis. To drive dislocation motion, I applied a constant force in opposite directions to the two fixed surfaces along the z-axis, and this shear loading mimics an applied stress and initiates glide. In the PBC simulation setup, shown on the left, periodic boundaries were applied in both the x and z directions. These boundaries approximate an infinite system by allowing atoms that exit one side to re-enter from the opposite. Periodicity in the x direction simulates a dislocation of infinite length, while periodicity in the z direction enables uniform shearing. The y direction boundary is fixed, holding atomic positions steady. By contrast, the free surface simulation setup, shown on the right, applies periodic boundaries only in the z direction. Along x, the dislocation terminates at free surfaces, which are exposed boundaries that disrupt the perfect crystal lattice. These free surfaces were created by adding vacuum regions between the crystal and the simulation box edges. Understanding these boundary conditions sets the stage for analyzing how the dislocation actually moves. So next, I'll walk through how I tracked the dislocation position over time in each setup. To begin analyzing dislocation motion, I ran simulations under applied shear stresses ranging from 100 to 1100 MPa. For each stress case, I tracked the average z position of the dislocation over time, and the two plots here serve as examples of the two distinct behaviors I found. The left plot shows a steady-state case at 200 MPa, where a single dislocation is maintained throughout the entire simulation. This results in a clean linear trend that reflects constant gliding velocity. By contrast, the right plot shows a higher stress case at 700 MPa, where the dislocation undergoes transient motion. It initially glides with a rough constant velocity, but the dislocation eventually breaks apart or multiplies, causing a sharp deviation from linearity. I'll explain the mechanisms behind this breakdown on the next slide. To better understand this dislocation behavior at higher stress levels, I used OREU to visualize the structure at different time steps and identified the steady-state single dislocation regime. This plot shows the 1000 MPa case as an example of where dislocation multiplication occurred. A single dislocation is clearly visible early on in the simulation, as seen in the linear portion of the curve and the OREU snapshot at time step 5000. However, after time step 10,000, the dislocation multiplies and breaks apart, as seen in the second snapshot on the right. By identifying the time step where this transition occurs for each stress case, I restricted my velocity calculations to the region where only one dislocation was present. After calculating dislocation velocities for each case, I plotted velocity as a function of applied stress for both PBC and free surface simulations. At lower stresses, both simulation setups show near-linear increases in velocity, reflecting steady-state motion, with free surface velocities being consistently higher. At 600 MPa, dislocation multiplication begins in both cases, and behaviors quickly diverge. While PBC velocities continue to rise and peak at 900 MPa, free surface velocities jump sharply at 600 MPa, then gradually decline. To help interpret these results, I included the two pressure-corrected limiting velocities for basal edge dislocations on the plot, which are approximately 2.6 km per second and 3.8 km per second. These velocities represent the subsonic to transonic and transonic to supersonic boundaries respectively, and were calculated at -5 GPa, the lower end of the expected pressure range. Several dislocations in the plot are transonic, and while one appears to be supersonic, it's too close to the limit to be sure. Without detailed analysis of the pressure distribution around the dislocation core for the free surfaces case, the limiting velocities there are unconfirmed. Previous research by Dong et al. Found that free surfaces do limit dislocation velocity in copper, but our current data for magnesium does not clearly support the same conclusion, so further analysis is needed to fully understand these results. To investigate why free surface simulations yielded higher velocities, we examined average pressures but concluded that the crystal likely did not expand in the x direction. Future work could involve running larger-scale simulations and checking the pressure distribution around the dislocation core, comparing maximum and minimum values between the PBC and free surface cases. Additionally, incorporating temperature effects could reveal new insights into how dislocations behave under different conditions. Thank you.